Okay, we will go through some important points in the class 12 physics chapter 14 semiconductor electronics materials devices and simple circuits. Okay, in earlier days we use vacuum tubes to control the flow of the electrons. Okay, three electrodes, four electrodes. So the vacuum tubes consume high power and operate at high voltages. So now the electronic systems made up of liquid crystal displays which consume less power. Classification: conductivity and resistivity. Conductivity is inversely proportional to the resistivity. That means more resistive means less conductance. Okay, so conductivity, so resistivity is inversely proportional to conductivity, or conductivity is inversely resistivity. Okay, you can say either way. Metals have the higher conductivity. Semiconductor is intermediate, whereas insulators have higher resistivity. Okay, metals higher conductivity, insulators higher resistivity, semiconductors in between. So the elemental semiconductor made up of silicon and germanium. Silicon atomic number 14, germanium atomic number 32. Both have the valence, 4 valence electrons. Okay, only the outer orbital is different. Okay, silicon 4 valence electrons in the second orbit, whereas germanium 32 is in the fourth orbit. That valence electrons, 4 valence electrons in the fourth orbit. So the energy of the electron is divided by which orbit that valence electron resides. Okay, the energy levels is divided into valence band and conduction band. The energy levels of the valence band is less than the conduction band. Conduction band is at the higher energy level. So in some cases these valency band and conduction band overlaps, and in some cases there is a gap. N means it's a number of atoms. See, normally this conduction band is completely empty at the zero temperature. At temperature is 0. See this conduction band, this is the conduction band, this is empty, no electron in the at temperature 0. This is the valence band, all electron lying in the valence band, and this energy gap between this conduction band and the valence band is the ionization energy, E.g. energy gap. Okay, here N is the number of atoms. Lowest energy level in the conduction band. Okay, lowest energy level in this conduction band. Highest energy level in the valence band. This top of the valence band, bottom of the conduction band. In between, this is the energy gap. At 0 degree Kelvin temperature they are given. So this is how the metals band, the energy gap between the conduction band and the valence band. In some materials there is a gap, and this is the overlap. Here conduction band and the valence band overlaps here for the metals. For the insulator, this energy gap is more than 3 electron volts. Okay, for the semiconductor it is less than 3 electron volts. So greater than 3 electron volt is insulator, less than 3 electron volt semiconductor. Intrinsic semiconductor, it is a pure semiconductor without any impurities, that is doping added. Each atom is surrounded by the 4 near neighbors. This is the lattice structure. See, normally the thermal energy ionizes only few atoms, okay, in the crystal lattice. See, in the intrinsic semiconductor, the number of electrons is equal to the number of holes, okay. Both are equal in the intrinsic semiconductor, that is without doping, okay, intrinsic semiconductor. So here the plus 4, this is the number of valence electrons. These electrons form covalent bond with the nearest atom, okay. This electron, okay, it can be silicon or germanium. So within this crystal there is a electron current as well as hole current. Total current is the sum of electron current and the hole current. At equilibrium, the rate of generation is equal to the rate of charge carriers, recombination of charge carriers. Okay, these holes are thermally, if you raise the temperature, then electron will get the freed and there is a hole is generated. Okay, thermally generated free electrons. Holes, here hole and here there is a electron, and in this structure you see the electron moves to the hole, and that place a new hole is created. This is at the temperature 0, no free electrons in the conduction band, all electrons in the valency band. But if you raise temperature greater than 0, if you heat, then there is some electron moving from this valence band to the conduction band here. Holes in valence and conduction band, okay, T is greater than 0. So those electrons actually came from the valence band here. Carbon, silicon and carbon have the same lattice structure. Both all are having the same valence number of electrons, but carbon is an insulator while silicon and carbon are the semiconductor. They are asking why. The 4 bonding electrons of the carbon silicon are respectively in the second, third and the fourth orbit, okay. The valence electron, all 4 valence electron means, but they are in the different orbits, okay. See here, this is for the carbon 12, this is in second orbit, okay. This 4 valence electron. Silicon, that is in the third orbit, whereas germanium, that is in the fourth orbit, okay. They are in the different orbits. This is 32 atom number 14,6, okay. They are in the different orbit, but they have the same number of valence electrons, okay. The ionization required to take out an electron from the atoms will be very less for the germanium, okay. That is in the fourth orbit, okay. So when you move, the orbit goes up, so it will require less energy to free that electrons, okay. Carbon is free electrons, valence electron in the second orbit, so that requires more energy to free the electrons. Hence, the transfer of electrons in the conduction of the germanium and silicon are significant but negligibly small for the C. So the free electrons in the conduction band will be very less for the carbon. So extrinsic semiconductor, the conductivity of the intrinsic depends on the temperature only. So okay, so now how to convert a intrinsic to extrinsic when small amount, say few parts per million of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manifold. Such a materials are known as extrinsic semiconductor or impurity semiconductor. So we are adding some impurity called dopants to the intrinsic semiconductor, then it will become extrinsic. Okay, these are the dopants. There is pentavalent, that is they have 5 valence electron. These are the phosphorus, arsenic, all these are having pentavalent valency 5. Okay, then there is a trivalent, that is aluminum is example of a trivalent. If you add a pentavalent, okay, this is the impurity, all these are the intrinsic plus 4. Okay, when you add a impurity, this is n type, and a new hole is created, new electron, free electron is available. Okay, extra electron, because it has 5 valence electron, this has 4, so 4 will form bonds with 4, then 1 electron will be free. Okay, that is this free electron. So this is n type semiconductor. Okay, here more electrons are free. This is called n type. Okay, so in n type semiconductor there are more electron than the holes. Okay, n type semiconductor. But in the p-type semiconductor, we are adding a trivalent impurity. Here you see this is impurity and these other things are silicon or germanium. That is in the crystal we are adding impurity here. Here there is a extra hole. Okay, here hole is, this is hole, extra hole. So in a p-type, the holes are in greater number than the electron. That is p-type. Acceptor and donor energy levels at equilibrium this. So these are the energy gaps in the carbon, silicon and germanium. Okay, energy gap values. So you see carbon has a higher energy in this. This is n type. Here you see there are more electron than the holes here. Okay, this is n type. And this is p type, here more holes than the electrons. Suppose a pure silicon Si crystal has these atoms. Okay, it is doped with 1 part concentration of the pentavalent. Is calculate the number of electrons and holes given that. Okay, now we are doping silicon with this As and compute the number of holes and electrons. Okay, see here this thermally generated electrons is much less than the doped electrons. Okay, so the number of electrons is nearly equal to the doped electrons. Okay, thermally generated electrons are negligibly small as compared to those produced by doping. So the doping contributes the more than the thermally generated. So doping electron greater than the much greater than the thermally generated electrons. Okay, then the number of electrons, number of holes, p-n junction. There is a diffusion and drift. Due to the concentration gradient in the p-n junction, p side have more holes and n side has more electrons. And due to this concentration gradient, okay, that means concentration varies. P side have more holes and n side has less holes. N side has more electron, p side has less electron. So because of this concentration difference, holes diffuse from p side to n side and the electrons diffuse from n side to p side. This is called diffusion. Okay, diffusion. This creates a electric potential in the barrier. So okay, This is electron diffusion, electron from here to this side, holes from this side to this side, hole diffusion, electron diffusion. So this generates a region called depletion region here. Due to this, there is a potential generated at this junction, that is called barrier potential. Okay, this is the motion of the charge carrier due to the electric field is called drift. Okay, this is diffusion and drift. Diffusion is because of this concentration gradient, holes and electron concentration difference, the diffusion takes place. Drift due to the electric field of this depletion regions. Okay, there is a charge here and this generate electric field. The drift of charge due to this electric field is called drift. Okay, that is called a barrier potential. Okay, potential difference here is called barrier potential. Can we add a slab of p-type semiconductor and physically join the another n-type semiconductor to get a b-n junction? Okay, no, that is not, we cannot just take the slab and make it. Any slab whosoever not will have a roughness much larger than the interatomic crystal spacing. That roughness is much larger than the interatomic crystal spacing, and hence the contact at the atomic level is not possible. It's just taking and joining the slabs. Okay, the junction will behave like a discontinuity for the flowing charge carriers. Okay, the charge carriers will not flow. Semiconductor diode, this is diffusion region, n side, p side. This is the symbols of the diode, p-n junction. Direction of the conventional current. Forward bias. What is forward bias? Across such that p side is connected to the positive terminal of the battery and the n side is connected to the negative terminal of the battery. Okay, p side positive terminal, n side is a negative terminal. So p side positive and n side, this is forward bias. The resistance of the depletion region, this is the resistance of the depletion region, a region where is a very high as compared to the resistance of the n side and p side. Resistance here, p side and n side is much less than this resistance here at the depletion region. So in the forward bias, the barrier potential is equal to the V0 minus V. Okay, this is the built-in potential V0 and V is the applied potential. This is V and this barrier built-in potential is V0. So now the difference, this is the barrier width V0 minus V. Effective barrier height, this one is the forward bias V0 minus V. Okay, this is the one without battery, with low battery and the high voltage battery. Okay, barrier height. So when more voltage is applied, the barrier height is reduced. Okay, barrier height is more when there is no voltage applied. So the width here is becoming less when you connect to the external battery. So that is important here. Okay, the barrier width is reduced. Depletion layer width, this width is reduced during the forward bias. Okay, when you connect positive to the p type and the negative terminal of the battery to the n side. So this is the reverse bias, that is we connect p type to the negative side of the battery, n type to the positive side of the battery, that is the reverse bias. Okay, in this case you see V naught plus V, that is the barrier height. So here forward bias V naught minus V, here V naught plus V. So that means this width will increase. Okay, this width will increase during the reverse bias. That is important. This width is increased during the reverse bias. This is forward bias. Positive is connected to the P side is connected to the positive, N side negative, forward bias. So the barrier width is reduced, but during reverse bias the barrier width is more. This is the reverse bias. Okay, this is the characteristic only when you apply the reverse bias. This is the forward bias. Okay, you see this is in microamperes, this is in milliampere scales. Okay, forward bias current will be more, that is in milliampere scale. This is in the reverse bias microampere scale. Okay, threshold voltage, dynamic resistance, VI character of the silicon, calculate the resistance of the diode at this current. Okay, the voltage, this is straightforward. So you can compute the resistance. So here there is no negative sign, resistance. Okay, current is negative, but resistant no negative sign here. Application of the junction diode. Okay, so here this is the circuit. We have a transformer here. To step down here 230 volt, we are stepping down the voltage. That is why we are using the transformer. Then we are connecting a diode. This is diode conducts current in the one direction only. So if you input voltage, this is the output voltage. Only this side it conducts, and this side it is a reverse bias. The diode will block. Okay, so now this input and output frequency will be same. How to compute the frequency? See, if you take a wave, this is repeating for this is one cycle. Okay, here 3 cycles are given, and let us say this time period for the one cycle is 1 millisecond. Then the frequency will be 1 divided by the period. Period is 1 millisecond. 1 divided by the period equal to 1 divided by 1 into 1 cross 10 power minus 3, 1 millisecond. So that will become when it come it will become 1 into 10 power 3. 1 kilohertz is the frequency of this wave. Now this wave also having the same repetition period. You see from here again it is repeating here. Okay, if you take only here different. Okay, how you is repeating we have to take. So here also for every 1 millisecond it is repeating. So this frequency also same as this. But here if you say a wave like this, that is repeating for every 0.5 millisecond. So if you apply the formula, then the frequency is double that frequency, that is 2 kilohertz. Okay, frequency is 1 divided by the period of the repetition. Okay, so now this is the input voltage. Output voltage also will have the same frequency, although negative part is cut off. Okay, this same period, this time is same in the output voltage also here, because it conducts in only one direction. So this negative side is clipped. Okay, it is not passing. This is called half wave rectifier. It is passing only the half wave of this sine wave. Okay, that is called half wave rectifier. So now if you take a full wave rectifier, you see the circuit. We have 2 diodes are given. Okay, so now in this you see complete wave passes. So here both side will conduct. Okay, so this is the output. So this output frequency is twice the input frequency. Okay, here one cycle period is this much time, here one cycle period is only this time. Okay, the output frequency is twice the input frequency here. Full wave rectifier. So we can use the capacitor to smoothen the output voltage. See, when you use the capacitor, it will become like this. Not many fluctuations will be there in the output voltage. Okay. These things are already seen the above. Exercise in in the n-type silicon, which of the following statement is true? Okay, in the n-type, holes are the minority carriers. Okay, n-type, the electrons are the majority carrier, and the pentavalent atoms. Okay, n-type. Okay, this is the n-type. Okay, we are using a pentavalent doping. So here the volts are the minority carriers. Okay, see n-type. Okay, the electrons are the majority carriers, volts are the minority carrier here. So here electrons are the majority carrier. Okay. Which of the statements given the exercise to for the p-type, that is ulta. Okay, so here for the p-type, volts are the majority carrier and trivalent. Okay, page number 9 for the p-type. For the p-type, okay, here p-type we are using a trivalent. Okay, here volts are the majority carrier. Carbon, silicon, and germanium have the 4 valence electron. They are characterized by the valence and conduction bond separated. So I already shown you the carbon free electron, valence electron in the second orbit, silicon third orbit, germanium is the fourth orbit. So this energy required to take out the electrons will be more for the carbon, and will be very less for the germanium. Okay, this is I already explained in this example. Okay, page 7. See here, this example I already given. Okay, in an unbiased PN junction, holes diffuse from P region to the N region because of the concentration gradient. Okay, P-type hole concentration P region is more as compared to the N region. This is called a diffusion. Okay. See, due to the concentration gradient across p n sides, holes diffuse from p side to n side and the electrons from n side to p side. When a forward bias is applied to a p-n junction, lower the potential barrier. I already shown you during forward bias the barrier will be reduced. V naught minus V. Okay, V naught minus V. We have to subtract the applied voltage from the barrier button. That is why it get reduced. Page 13. See here, this get reduced. V naught minus V. In the half-wave rectifier, what is the output frequency if the input? Okay, I already showed you half-wave rectifier. Output frequency will be same as the input frequency, but for the full wave rectifier it is doubled. Okay. See, for the half wave rectifier, this is the input frequency. This output frequency, this is same as the input frequency because the wave repeated with the same time interval. This is the one cycle. This is here also one cycle repetition in the same time interval. So frequency will be same. 1 by t. 1 by period is the frequency. But if you full wave rectifier you see, here the frequency, here you see the time is half of this time. Okay, for let us say this is 1 millisecond, means this is for every half millisecond it is repeating. Okay, so the 1 by time is the frequency, so frequency of this is double the frequency of the input voltage. Okay, for the full wave rectifier. Okay.